In this lesson, we're going to focus more on heat capacity. What do we do if an object has a fixed mass? In our previous examples, we looked at water and sand, and we were given the mass of those, but any particular sample of water and sand is not going to have the exact same mass, no matter how careful we are in measuring it. And so the mass changes easily. When we look at an object, such as a spoon, the object doesn't change mass on a regular basis. So that spoon is going to have the same mass. Even if I do 10 different experiments, it's going to have the same mass. And in that case, instead of looking at specific heat capacity, we're going to look at heat capacity. And this is the energy needed to raise the temperature of an object of a substance by 1 degree Celsius. We're no longer looking at raising the temperature of 1 gram. We're looking at raising the temperature of the object. And when we look at the units for heat capacity, we see we have joules per degree Celsius or calories per degree Celsius. Notice that the grams are missing from the denominator because we're not looking at a specific mass of something because this object isn't changing mass. So we talk about the heat capacity of the object. So something that changes mass easily, we use specific heat. For an object that doesn't change mass easily, we use the heat capacity. And we have a different equation here to calculate the value when we're dealing with the heat capacity. Notice that it's Q equals C delta T. Q is still the heat. We no longer have mass in there because we don't have the mass and we don't have grams in our heat capacity value. C, without the subscripted S, is the heat capacity. And then delta T is still the change in temperature. And it's a state function, so that is TF minus TI. Now we can plug the values in to our problem. We have 100 joules equals 79.5 joules per degree Celsius. Notice no units of grams in this value. We have TF, that's what we're trying to find, and our TI is 22 degrees Celsius. I'm going to divide both sides by the 79.5 and get 1.26 equals TF minus 22. Add 22 to both sides and get 23.26 equals TF. And then TF equals 23 degrees Celsius when I round it to the correct number of significant figures. Specific heat capacity and heat capacity are very similar, but that key difference, having the grams in my specific heat value, lets me know which equation I'm going to use. If I have grams, it's MCS delta T. If I don't have grams, it's C delta T. One of them is for raising the temperature of 1 gram of a substance. The other is for raising the temperature of an object by 1 degree Celsius. Let's look at another example. A 15 gram, see the word unit gram in there, block of 10 with our specific heat of 0.213 joules per gram degree Celsius at 50 degrees Celsius cools to 31 degrees Celsius. What is the change in heat in joules? Notice that we have grams in our specific heat and we're given the mass of a substance in grams. And that lets us know we're going to use the equation Q equals MCS delta T. We're trying to find the value of Q, and we know the mass is 15 grams. Our specific heat of 0.213. TF is 31 degrees Celsius minus TI, which is 50 degrees Celsius. Notice it's not always the bigger value minus the smaller value. It's final minus initial. We're seeing that this block cools to 31 degrees Celsius. So it's ending at 31. It starts at 50. Now we can do the calculation and we get Q equals minus 60.7 and we round that to minus 61 joules. And the value of the 61 tells us how much heat. The negative sign tells us that heat was being lost from the system to the surroundings. Let's look at a different type of problem where we're not actually given values except for the specific heat. 2 blocks of metal, 1 gold and 1 copper with the same mass and at the same temperature. The same amount of heat is applied to both blocks. Which one will have the higher final temperature? Look at our equation, Q equals MCS delta T, and determine which metal, gold or copper, will have the higher final temperature. Notice we have the same mass, same temperature, same amount of heat. The only thing that's going to be different is our delta T. When we look at our equation, we see that as CS increases, delta T must decrease because Q and M have exactly the same value for both substances. So in comparing these, if Cs goes up, delta T must go down. We have the same initial temperature, and what we're looking for is the substance with the higher final temperature, which means our delta T is going to be bigger. If we want a bigger delta T, then we need to have a smaller value of the specific heat, because those two values are inversely proportional to one another. Therefore, gold is the correct answer. It has a smaller Cs, so it's going to have a larger delta T and will have a higher final temperature. 95 joules of heat is applied to a 12.5 gram block of aluminum initially at 24 degrees Celsius. What is the final temperature? Notice that we have grams in our specific heat value, which indicates which equation we need to use. We have Q equals MCS delta T. Plug in my 95 joules, my 12.5 grams for the mass, my specific heat of 0.903 joules per gram degree Celsius, TF minus 24 degrees Celsius, which is our initial temperature. I'm going to multiply 12.5 times 0.903 and get 11.29. I'm going to divide both sides by 11.29 and get 8.41 equals TF minus 24. I add 24 to both sides and get 32.41, and then I round that to two significant figures. TF equals 32 degrees Celsius.